Stuff. Thank you everyone for coming to AI and Deep Learning for Enterprise number 14. We are a meetup all about applied AI. Just before we get started, we've got a couple of quick bits of housekeeping. First things first, a massive thank you to Datasparq and their team for looking after us this evening. We're really lucky to have them hosting us and providing all the food. So unfortunately, Naomi was ill this evening and couldn't make it, and I have not updated the slides, but I'm Hugh. I'm an organizer at ADL, which is this meetup. If you have any questions or need any help this evening, give me or one of the Datasparq team members a shout. Get to the next slide. So we have some great talks for you this evening. We have Ramani from Datasparq, who's talking about geospatial information systems. We have Tom Scott from Streambased, talking about building real-time data models with Jupyter and Streambased. Michael Natusch, who is talking about real-world AI at survey practitioners, which is particularly exciting, I think. A couple more quick things. So we have a code of conduct for all of our events. Short version is we want to create a space where everyone can feel welcome and safe and participate. Long version is available on our website if you want to scan the QR code. It's also available on the meetup. We have a Slack community now that's opened up as of today. So if you want to keep super up to date with what we're doing and hear about events sort of in their early stages, you can join there. And if you are waiting outside and there's no one there, you can also message on Slack and get that in. Cool. Without further ado, I'm going to hand over to Ramani.
Hello, everyone. My name is Ramani. I work at Datasparq, and today I'm going to talk to you about the world of geographic information system. So, what is GIS, or Geographic Information System? It's any system that captures, stores, analyzes, manages any data that relates to any point in space. So quite a broad kind of field, and you'll kind of see it cropping up in lots of different places. You know, you might even think in your own lives or in your own organization's examples, you know, maybe you work with buildings or you work with parks or roads. All of that data is GIS data. Data also is foundational to any AI or deep learning or data science that we do, which is why I thought it would be a great opportunity for us to explore a little bit more about what geographic information system is, the data that it contains, and kind of get some juices flowing on how we can use it in our lives. So, just starting off with a few examples of GIS from history. Some of the first examples actually came during the cholera outbreak in Europe. The cholera outbreaks killed a lot of people, and the first example was when a physician actually created a map outlining all of the districts in Paris and the number of cholera cases per 1,000 that were in each of these cases. Suddenly, instead of just seeing numbers with like kind of street X or district Y, you could visualize that data. It was a visualization of the world that you were used to seeing with data that you needed to avoid getting cholera. And also dealing with the outbreak as well. A few years later, John Snow, who was a physician and an epidemiologist in London, actually took that one step further. He plotted out where all of the cholera cases near Soho had been detected, and actually looked at what water sources were nearby. It seems quite intuitive now. We're so used to working with so many different data sources. Of course, if you know that cholera comes from water and you have cholera cases, you would combine that data to figure out which water sources were causing cholera, but not in the 1850s. And this was revolutionary. Suddenly, they had a way and a method of pinpointing which water sources were causing cholera. And for me, I think this really encapsulates the two strengths that GIS has. The first is taking data that might just be numbers that we're used to seeing and actually turning it into something that people can digest through visualizations and putting it on a representation of the world that they are so used to seeing. And then the second is actually doing a risk analysis. We all live and our lives are, you know, at these various points on land, and we are affected differently based on where we are. So, with that in mind, I thought it'd be a great opportunity to cover some of these basic concepts in GIS. You know, what do you need to keep in mind if you want to actually start including geospatial data in your organization? And the first is the idea of projection. So maybe some of you remember it from maths class in school, but projections is basically a way of mapping one thing onto another. In this particular case, because we're working with land, it is the globe onto a 2D surface, like a map. Unfortunately, I don't know if any of you remember this from maths, but there is no simple, trivial way of mapping a globe or a sphere onto a 2D surface. However, there are multiple imperfect ways of mapping the globe onto a 2D surface, and you can see kind of the three broad categories in which this can be done on the diagram there. You have planar projections, which projects your sphere onto a plane, mapping each point. You have a conical projection, which essentially rolls out your globe like a dosa, if any of you have had one. And then the final one is a cylindrical one, which is rolling it out like a burrito. In each of these cases, you end up having distortions that occur. So you can have distortions that occur in one or many or all quantities of like area, shape, scale, distance, and angles between points. So the first thing to really keep in mind when you see a map is, what is this map telling you and what is it trying to preserve? The map that we're most used to seeing is something like this, the blown out version. It is a map that was created for naval transport. And so of course, it wants to maintain angles. When you're on the sea, you don't want to figure out if the angle has changed from the map to the point you are on the planet, because it's not very helpful, and they had even less technology back in the day than we do now. And so that's what it meant to do. And so it used the cylindrical projection. But what it does mean is that it actually gives us a very distorted idea of the area that the different countries cover. For example, Greenland, as you can see, this massive blob on the map is represented 550 times bigger in area than it is in the real world. Now you might be thinking, sure, it skews my mental map a little bit, but why does it make a big difference? It makes a big difference when you start putting data on it. If I was to then start putting, because as you can see, there's a little grid here. If I was to say, let me look at the per capita per grid on that map, it's suddenly going to start looking very skewed and looking like it's going to seem that these big countries up north are very empty on this map. Not particularly because they're more empty than maybe other spots, but it's because that area has been stretched out. And so the representation of the population you have in those areas is far smaller. A good geospatial scientist will always have to keep in mind what the data is represented on and what they're trying to communicate. And that, I think, is something that everyone needs to keep in mind when they use GIS. The second concept is that of latitude and longitude. So when we flatten out the globe onto a 2D surface, it helps us put things like angles and distances and areas on it. But something that we're also quite familiar with is this idea of latitude and longitude. These are spherical coordinates, and they pinpoint actually exactly where on the Earth you are. That's very good for, as I said, pinpointing where you are, but not very useful in the real world. I can't tell you, go 0.2 degrees latitude that way, and you know exactly what that means. And honestly, the distances that latitude and longitude cover vary as you move away from equator. So you can't just approximate these values to say, oh, a 0.1 degree latitude is 10 kilometers, because it's only 10 kilometers at the equator. When you're looking at geospatial data, you'll also see something that says WGS84. This is the code that is used to represent latitude and longitude. This brings us kind of circling in the same concept to what is probably the fundamental idea in GIS, which is that of coordinate reference system. Coordinate reference system now takes this 2D thing that you have and maps it back to the globe. So how can we take this 2D map that we have and map it back to the globe? You might be thinking, well, you've shown us that there are many imperfect ways. There are about 3 different types of projections that you've shown us. Let's say there's maybe 5 or 6 different ways of imperfectly mapping data. Within that, there must be, 10, 20 different coordinate reference systems. That's not true. There are 5,800 different coordinate reference systems that exist that are either in use now or have been in the use in the past. So some coordinate reference systems also deprecate over time. Why do we have so many coordinate reference systems? So the projections that we spoke about are at a global level, but very little of the work that we do actually is at a global level. Say you're only working with the UK. If you know that you're only working with the UK, it doesn't make any sense to have the errors of trying to map a fully curvature globe onto a 2D surface. Let's just focus on the smaller curvature of the UK and map that on. But now what if you work in Hertfordshire? You don't want the errors of the UK in your dataset. So then you just map Hertfordshire onto a 2D surface. And as you can imagine, this slowly balls out of control as everyone's like, I want my data to be as perfect as possible, minimize the errors as possible. And so you end up with thousands and thousands of coordinate reference systems. When you start working with GIS data, it is crucial to understand what coordinate reference system you're working in and what you want it to do. You might, and sometimes it's quite deceiving, right? You can plot your coordinate reference system and it will show you a visual representation of the world as you're used to seeing. And so you go, perfect. This is fine. I can just do my calculations on it, do my aggregations, do my statistics on it as I expect. However, if the underlying assumptions that have been made slightly break even what you're trying to do, then you will end up with imperfect results. So, where can I find out about my coordinate reference system? Well, the European Petroleum Social Group actually went about collating all of them because they realized that they were working with all these coordinate reference systems across the world. And you can find them with their associated EPSG codes on the EPSG website. It's quite an informative data set. It will tell you what units your coordinate reference system is. It will tell you what your geodetic CRS is, which is latitude and longitude in this particular system. It'll give you some more information. And then it'll actually give you scopes, remarks, as well as area of use. As I said, coordinate reference systems can be made for very specific areas. And so you need to be aware of what areas your CRS is valid over. Just because your dataset, just because you have a dataset that is in the UK and you have a CRS on it, you can't just superimpose the German data on top of it or say, oh, the German data can be on the same grid as the UK data if they have vastly different coordinate reference systems, and they can't always map in between each other. So now that we're kind of familiar with this idea of taking our globe, mapping it onto a 2D surface, where does the data come in? There are two major types of data that you will find in GIS. The first is raster data, which is also found in image processing. In this, you have a grid, and the grid, each point in the grid has a value. As you can imagine, because you're working with the globe, which is a continuous surface, your grid is going to end up having approximations. So in this particular case, you have a raster data of what is considered trees, but you can see that the trees don't stop just because, you know, the grid says it's done. It's just that the proportion of trees in that area compared to the grassland is now changing. But it does mean that you can have this data set available over larger regions because, as I said, this is visual imagery data or just imagery data, really. And so you can have satellites collect this for you. You don't need to have a person in there going. You can build an algorithm to identify what is forest, what is grassland, and then apply it over your entire massive global data set, and it's fine. I'm not saying that sending a satellite up into space is low effort, but generally, you know, it will give you a global data set if you wanted. The second type of data set is vector data. Vector data helps us actually capture the continuous world. So there are a lot of different kind of subtypes in vector data. You have points, you have lines, you have polylines. This data is far more resource intensive to capture. You need to have either manually someone go to capture the areas or the bounding boxes or the polygons of whatever you're interested in. You can use remote sensing data and raster data to compute vector data. For example, this is maybe a vector around a feature that I'm interested in, but the most accurate and precise data that you are going to end up getting is by using human resources. I think this throws up a really interesting point around ethics as well. So we have one set of data that can be available over larger regions that is collected by a resource that is probably, like satellites, not just one country sends them out, but usually are a coalition between multiple countries versus something like vector data, which requires you to put time, effort, resources, and stability into collecting them. And when you're creating something using GIS data, it is very vital for you to understand where else could you be using it. Are you only creating a model on a very data-rich region? Because we're quite data hungry. We want to have the best data to create the best model. But what are the implications when you apply that model onto a data-poor region? Do we want to create this segregation between data-rich regions and data-poor regions to get even worse? Because now we're also creating models that work better on data-rich regions. And I think that's definitely a question that each organization needs to answer for themselves based on kind of what the problem they're trying to solve is. So GIS has a lot of use cases, as I said. My personal favorites fall in the ESG category, which is environment, social governance, to measure deforestation, leaks, water management, to aid in reporting like diversity, to do community engagement through visualizations, to help in humanitarian crises. When the Turkey earthquake happened, some of the GIS images that came out first were actually used to go on the spot to provide aid in the areas that were most affected. And with this, we're going to go through an example of what does it now look like to actually have GIS in your organization. So you have a person who's come to you, you are maybe a consultancy, and they say, I manage a lot of properties in California. I know that California is a wildfire-prone region, always known it, but over the last few years, things have gotten really bad. And I just want to understand, at least right at the bat, what properties are the most exposed to wildfires? What can I start doing to actually protect at least the properties that are most risk, which goes back to what John Snow did, connecting GIS to risk. This brings us to first getting a GIS scientist or an earth scientist into your organization who actually understands what wildfires are and has spent multiple years trying to understand how wildfires behave. For a wildfire to happen, you need the perfect kind of combination of things to occur. The first is that the weather needs to be particularly dry, particularly warm. The wind needs to be in your favor to push your fire as it happens into areas of more fuel. You need to be in a place where the slope allows for the fire to move, and certain slopes allow for more drying to happen. And finally, you need to actually have fuel, right? Right in the center of London, it could be very hot, it could be dry, it could have low humidity, but you will never have a wildfire because there's nothing to burn. And that fuel piece is what we'll be looking into a little bit. We also need to understand what is crucial for us to understand risk. So risk is made up of three things. You have your hazard, in this case, wildfire. You also have your vulnerability to hazard. So are you in a log cabin or are you in a concrete building? They have different vulnerabilities and different kind of chances of being affected by the wildfire. And finally, your exposure. As I said, are you in the center of a city or are you in the middle of a forest? You are exposed to different wildfire risks. And going back to what our person said when they came to us with a problem for wildfires, they said, I know I'm in California, it's a high hazard region, we've got that hazard covered. All my properties, they didn't say this on that page, but all my properties are similar, same vulnerability. I just need to understand how exposed they are to wildfires. How what is the fuel presence like around my properties? Here is what their properties look like. It's a very nice example of putting vector data onto a map. As you can see, this is OpenStreetMap, so the same CRS that we've come across before. And already, this is giving us an indication of what, we might hypothesize which properties are at high risk and which properties are at low risk. We can see that some of them fall in a greener area than others. We know that green usually refers to grasslands or green areas. And so, yeah, those are more likely to burn. We're also going to talk a little bit about remote sensing. We're going to take a quick detour. So as I said before, we want to create an equitable algorithm, and we want to create an equitable system. This person's come to us from California, and California actually has really wonderful wildfire detection and management systems. So what you can find, for example, is actual shape files of where wildfires have happened and how much they've burned. But we're going to say, this person's come to us from California, they can afford to pay us, which is very nice, but I want to create something that everyone can use. And that means that I'm resorting to using remote sensing data. The way that remote sensing data works is that you have a big sensor that goes and takes pictures of different points on the planet. The points that it's taking pictures of usually have had sunlight on them. So it's looking at a vast range on the electromagnetic spectrum. So all the way back to the physics lessons so we used to have. It takes all these pictures, it goes around and around the planet, and this leads to two things. One, the spatial resolution, which is how fine the detail on the ground can my satellite detect? And then the second is temporal resolution, which is how long does it take for my satellite to go from come back to the same place? There's a trade-off in remote sensing, which is that the finer your spatial resolution is, the longer it takes for your satellite to come around. Because as you can imagine, it's taking longer and longer to take each of these pictures. And the coarser your resolution is, the shorter your temporal resolution. So again, a choice that needs to be made, a trade-off that needs to be made. Your GIS scientist has gone off, they've done the work, they've figured out what they want to do, and they've come to we're going to come back to that one. They come to an answer. They're like, great, we found a satellite that gives us a great balance between the spatial resolution that we need and the temporal resolution that we need. And it's this one called MODIS. MODIS is a satellite that goes around, and it has spatial resolution of 250 meters, which means that the raster data have a grid where each length is 250 meters. But it has an amazing temporal resolution of around 1 day, which means that kind of the two satellites that make up MODIS will arrive at the same spot once every day. This is really helpful if we want to, for example, detect active fires. There is a sinusoidal grid tiling system of non-overlapping tiles. So if I'm interested in California, for example, I'll find out which tile my property is that I'm interested in and just go pick that out. And that should be my data. As you can see, the whole globe is kind of split up over these 17 by 35 tiles. So each tile is actually quite big. And the data within it is at 250 meters resolution. So there's a lot of data in there. And that makes it very hard for you to read locally. As you can imagine, if I'm working with a year's worth of data, I couldn't open it. And you're only interested in quite a small subset. Moreover, the way that these satellites capture imagery is that they will go around, but they don't take images in perfect, perfect non-overlapping tiles in this particular case. The tiles will overlap. And so if you were manually going onto the MODIS website or using their API, you will have to identify which tiles actually cover the bounding box that you're interested in. As you can see, California kind of falls across two in this case. You will have to find a machine big enough to open them, and then figure out exactly what bounding box you're interested in, take that data out, and that is a huge computational challenge. And it puts remote sensing a little bit out of the hands of a person who might be interested. Until recently, this is where we go back, there was an introduction of this thing called a stack catalog. And a stack catalog actually does all of this computation behind the scenes. And so there is an API or a way to interact with it in Python. And you basically say, I'm interested in this particular file or this particular product. This one is from Microsoft in their Microsoft Planetary Computer, but you also have a similar product that's offered by AWS as well. So you can find one, find the remote sensing data in kind of from whichever provider you're using. You would go to the Fire, you would say, I'm interested in this, and it would do everything for you. It would mosaic the data for you. It would find you the bounding box that you need, and it would also do the coordinate reference system transformations for you. So you as an end user in this luxurious world with Stack actually don't need to think about all this coordinate reference system stuff that I was talking to you about earlier, but it's still really useful to know because it matters when you're using it at the end. So that's why I say CRS transformation can happen at any point in this process, and it just depends on your use case. So what does our wildfire data look like? We've taken our wildfire data for the same region in California, and as you can see, there's a lot of values. Cloud is a big one, and the bane of all remote sensing experts. Clouds ruin your data because you can't see anything. Your sensor is completely blind to what is underneath. So even if you are working with a satellite, for example, that has a temporal resolution of 1 day, if it's blind to what is happening underneath, maybe because of the monsoons or just because of the weather conditions. I mean, the UK is horrible to take pictures of because it's always cloudy. It's not going to give you that much data. Luckily for us, California, very dry, barely ever rains. So yeah, you can see the wildfires there. You can see the sizes of the wildfire as well. You have some very big ones kind of in the middle, and then smaller wildfires as you kind of move westwards. But the true kind of use comes when you now can combine the two data sets. As you can see, there's like the spatial reference to make sure that we're in the same coordinate reference system, and now we can see what our properties look like when they're superimposed on top of wildfires. And you can see that a few properties do fall in wildfire regions because we're working with quite a lot of properties over a large piece of land here. Visually, it's not always very clear. But we know the wildfires can have far-reaching impact, so it's not just whether your cell burned or not. I'm sure if you, especially because we're working with raster data and it is discretized, it might say that your pixel didn't burn, but maybe 40% of it burned. So we want to actually kind of create a little buffer of where wildfires could have an impact. We've chosen this to be 500 meters. And again, I think this is where subject matter expertise could really come into play. If you have a property management expert who says, actually, I'm okay with wildfire being 2 centimeters away from my house, at that point, it's a danger. You can change that. And it also allows us to kind of extend a little bit of our understanding from just being fires to smoke as well. And so this is what our data looks like using the buffering functionality that is available in Python. Finally, we're going to talk about the fuel aspect of it. So as we said, now we know where our properties are. We know whether they've burned in the past or not. But we don't know what they're burning. Are our properties only burning bare land? Are the wildfires only happening on water? We don't know. We probably think not, but we should be sure. So as I said, again, we're trying to create a global product, and for that, the best kind of your GIS scientist goes off, tries to find the best land cover data. And they find that there's actually one that gives you 10 meters resolution annually. It tells you what the coordinate reference system is, but again, we're quite lucky because this data set is available through the Stack catalog, and so they can just add it through their workflow without thinking too much about it. But as you can imagine, you now have a land cover data that is 10 meters resolution, so you're going to fit 25 by 25 different land cover pixels in one wildfire cell. Because your wildfire cell is now coarse, you don't really know where the wildfires happen. So you might be saying to any algorithm that you fit, everything in that 250 meter pixel burnt the same, which is not really true. But at the same time, wildfires are not the kind of thing that is just, static, and it doesn't just stay in the 10 meter pixel where it might have happened. It can spread. So also, you can't really say that only these 10 meter pixels burned, but ignore the impact of it on all these other ones that also belong in your 250 meter grid cell. And so this brings us to resampling, which is quite an important concept. As I mentioned earlier with remote sensing data, you have a lot of different spatial resolutions. And not only are you trying to match the coordinate reference systems that they are in, but you're actually trying to match the spatial resolutions to make sense of the data. How else are you going to piece it together? And it is crucial to, again, do this in the right way. There are lots of different ways of resampling. If you were to just, go on raster.io, which is the Python package that you require to do this resampling, it'll give you 4 different options. And, without thinking about it, you might go, great, average sounds good, just calculate an average. But what is your data saying? We're looking at land cover data. And what is the average between grass and water? Just because we have numbers doesn't mean that averaging those numbers makes sense. And so in this particular case, the 2 that are viable options for the categorical data that we have are nearest and mode, or majority. So what is my modal class in whatever I'm trying to resample into? And what is the nearest class to the center of the pixel that I'm trying to resample to? As you can see here, the impact of what the 2 different types of resampling look like. For nearest neighbor, it just finds whatever the central pixel is. And it's actually not very representative of what is actually happening broadly within that pixel. Whereas using the modal class, you are understanding a little bit more of what is happening in the pixel, as I said. With wildfires, again, this is very important because it's not a static feature. You can't just say that the wildfire only happened for this, or only the central pixel defined the wildfire behavior. It is very much what is happening in the continuous landscape that is kind of underneath it. So your GIS scientist goes off, they get the land cover data, they do resampling over it, they match it to the land cover, the wildfire data that they have, and they match it to where your properties fall. And leading to something, this is what your land cover data looks like. As you can see, the green areas are ones that burned, or ones that can burn. We know the trees burn, shrubs burn, grasses burn, shrubs burn, built area rarely burns. And this is what it looks like. So quite a simple table. After all of this analysis, you've gotten to a very simple table that looks at 3 different years, and it looks at all the properties you have, and it says, did my property fall in a pixel that burnt or not, and whether that pixel was flammable or not. Now, you can see that the number of properties that fell in flammable pixels is much smaller than the ones that didn't, which makes sense, right? The whole of California is not burning down, or the house in California is not burning down every year. Only a few of them do, but it's still not great. What you can see is that the proportion of properties that did fall into wildfire regions the likelihood of a property falling in the wildfire region was increased by the fact that it was surrounded by flammable land cover classes around it. Now this is very simple. You can now give to your property manager, here are the 950 properties that fall under these flammable classes, look after them first, do the wildfire management techniques that you need to do around them first, and then you can look at the rest of your portfolio. The rest of your portfolio isn't safe, but it is safer compared to these other ones, and you're already giving more information than they had. We can now bring data science and AI into it by actually now looking at what these relationships between the different classes looks like with areas that have burned, and also combining that with weather data and with topographical data to actually create a more rounded understanding of wildfire risk in this region, as well as all over the world. So that is it. Thank you very much. Bye.
Sweet. So in that case, I will introduce our next speaker this evening, Tom from Streambased. Thank you, Tom.
Thanks. You haven't heard what I'm going to say yet. Yeah, as Hugh says, I'm Tom from Streambased, and I'm going to start with a couple of apologies. So apology one, I like to walk around and wander around. I'm going to do that. And apology number two, I'm not a data scientist. I'm the enemy. I'm on the other side. I'm more of a data engineer stroke distributed systems engineer. So what I'm going to do for you today is I'm going to talk a little bit about Streambased and the possibilities of real-time data. So I have brought a data scientist with me. This is Pradeep. He's going to take over and show some super sexy data science stuff a bit later. But before we get into that, I'm going to frame it a little bit and hopefully get you a bit excited about some of the things you can do with real-time data. So I always like to start with a poll, and I love audience participation. Please don't hold questions to the end. Please shout, throw things at me, and I do love a good heckle as well, so go for that as well. So, but hands up if you think you're using real-time data in your daily life today. I mean, there's one for definite sure. One, and no Q as well. 2, 3, not too many. Hands up if you'd be surprised to find out that most of the data sets that you're working with today are at least eventually at the beginning of the chain sourced from real-time data. No surprises. See? And this is it.
I didn't follow your question, I'm sorry.
So I log in, I'm going to write a bit of SQL, and I'm going to run it against my data lake or my database. How surprised would you be to find out that that data set was created from real-time? 0. Perfect. That's exactly what I mean. And that is surely the case, right? If you're on a modern company, you are running with a real-time data that's providing an operational capability to your business. I'm going to dive straight into Apache Kafka, which is the poster child for this real-time data systems. Hands up if you've heard of Apache Kafka. This will be much more. Ah, brilliant. See, it's everywhere. Everybody knows about it. And so when I say what is Kafka, I don't really need to do it. You already know it. But I'll keep it short. What is Kafka? In short, it's the glue that sticks your business together. It handles the operational side of your business. If you have any kind of front end or any kind of downstream system, it's most likely that the communication between those components is handled by Apache Kafka. And it's my talk, so I can make these assumptions. Let's say we're all good boys, we've done the data mesh thing, we've implemented our microservices architecture, and if you have, Kafka is a core part of that operational workload. And it's everywhere. This is this beautiful microservices architecture. There's some big names in there. You can see a Heroku. LinkedIn and Uber are like the poster childs for making this stuff work nicely. And when it's done properly, it's an amazing tool. If you think about it, if you talk about events rather than chunks of data, as you would do in these event streaming applications, what you're generating is a changelog of everything that's happening in your business. An incredibly powerful tool. To give you an idea of how that works operationally, it looks something like this. We have our glue, Kafka, stuck in the middle. We have our nice, narrowly scoped and well-designed services that are interacting with this, and Kafka is providing message data to be. These services work together to solve your business problems. Go for it. Speaking of solving business problems, if you haven't got a bike, you can't get home. No worries. And the problem that I should give you a bit of background. I joined Confluent very early. I've been doing the event streaming thing for a good long time now. And if all of it is working well, it's basically invisible. So let's take the lid off it a little bit and do a bit of a worked example about how one of these interactions may work. I'm going to take the textbook case, your Revolut, your Starling, your Monzo, some of these banking apps, anything like that. And what I'm going to do is I'm going to get my phone out, I'm going to tap it on the Oyster thing. I'm northern, so this doesn't make any sense to me tapping it on the Oyster thing, but right. And what it's going to do is it's going to generate a transaction. We've got our transaction sitting over here. This is an event in itself, and the event encapsulates all the data that is involved in that transaction. It may be sent to via Kafka, and it's then sent to maybe one or maybe more than one service for processing. So here you can say, I'm sending it over to my settlement service to make sure that the guy on the other end is willing to accept this transaction. And but I'm also sending it over to my fraud service. Right? And these services individually will generate messages to react to these events, and they'll generate their own events that will go back to a third service, a balance service, that will update my current balance in my Revolut app. Right? And then finally, if all of these events are kosher and everything, we will get a further event that goes back to the banking app and does it. Now, why am I showing you all of this? It's very interesting, I'm sure, but how is it relevant to your daily life as a data scientist or a data analyst? Well, typically the amount of data that would be surfaced to you is about that bit. You would see this line, right? To you guys, this would be I made a transaction, it was confirmed. That's what would flow down. But you've lost all of this detail here. Right? And there's some very, very powerful insights that comes from this data. That's kind of principle number one. This talk is all about the insight that we've lost by ignoring real-time data. So if we move on, I'm just going to pause here quickly to give you a quick glossary because I'm going to start using these terms interchangeably. Where I say message, you guys are all from the database world, happy with this. Where I say message, think row, right? That's what it is. It's an encapsulation of an event. Where I see topic, think table. It's a logical organization of rows or messages. And where I say field, think column. Right? That's the one. The one differentiator I do want to make is when we're talking about topics rather than tables, these are append-only ordered logs. These are not, there's no concept of an update insert in the middle of one of these things. This is a time series that starts from back here and ends up here. Okay. So let's move on to how you'd normally surface this. Right? We've spoken about no one's surprised by this because everybody answered the question that they weren't surprised already. Typically, you have your operational side of the business here. You have your analytical side of the business over here. You have old me as a data engineer sitting in the middle, and never the two shall meet. Enemies from dusk to dawn, we're never going to like those. And yeah, what happens is your operational side runs the real-time data. It goes through some kind of ELT process. It gets surfaced into your data lake database, and that's where you consume it, and that's how you consume it. Except there are a few problems. Barely much actually goes through. And if something new happens here, you have to talk to me, the enemy, as the data engineer, in order to make sure it happens here. So you lose visibility on it. That's point number two for where you're losing benefits on real-time data. There's just so much more of it, and it's so painful to get at. What we want to avoid is this link here with analyst, data engineer, where analyst tries to describe a piece of real-time data that they have no access to see. It's not in your catalogs anywhere or anything like that. Data engineer tries to build a pipeline for that, but he's not interested in the data. He's interested in getting it from A to B. Right? So he builds the wrong thing. We go and just try and describe it a little bit better. Then we build it a little bit better. We go and describe it a little bit better. We eventually get something usable, and we've forgotten why we wanted it in the first place. Right? That's the fundamental problem that we wanted to address at Streambased. So this is where it starts getting exciting. But before we get to that, there's another problem that we get. We've got to think about what's lost in the pipe. We have our ELT process, and typically, instead of taking a one-for-one event to row mapping, what we do is we do an aggregate, or we do an update. The example here is perfect. We're still staying with my banking app. I've deposited $10, then $15, then $30. If we sit the EL2 in the middle here, what we're going to end up with is an account ID and a current balance, but the balance gets updated to 25, and then it gets updated to 55, and the history of how we got there is completely lost. The point I'm trying to make is that in many cases, it's the real-time system that contains the history of how you got to a current state. So a visibility on top of that real-time system would give you a lot more options in terms of that. So what do you get if you do have visibility on the real-time system? Well, you get a DeLorean. You get the ability to time travel. If we go back to my previous assumption that your real-time system is a changelog of everything that's happening in your business, it makes sense that you can slice it at any given time period. You can replay every event that leads up to that state and build up the current state of your business at any time period. That's great and that's fun. But what's even more powerful is you can then play all the events post that and see the consequences of the things that led up to those states. So if you're trying to make predictions or strategic decisions or things like that, it's this kind of data that's much more useful to you than, say, what we had previously, which is just our current state here. So that's what we did, by the way, that stream-based. What we did is we surfaced the real-time data that you're used to from Apache Kafka, and we surfaced it as the kind of interaction that you as an analyst or a data scientist would be completely used to. We speak SQL. We integrate with Superset here, but why not bring your Tableau, your Power BI, your Jupyter, as we're going to do in a minute. All right, and we make sure all of these integrations are there so that you can work with it, with your real-time data as it would any other kind of data local database system. It's the same tools, the same languages, and the same techniques. One of the core principles we started with is we don't want to change the way people work. We just want to open this new floodgate of data to. So close. That's what we did to begin with. We were nearly there. But if it was that easy, I suppose the plethora of data lake products wouldn't exist right now, right? Sadly, it's not quite that easy. The problem with this, doing things in this way, is that for most things from an event streaming system, you have to start at the beginning, read every single event, and go to the end. This is fine when it's sort of an hour's worth of events and you've got, say, I don't know, 1 million events sat in a small event sat in a topic. That's great. What happens if we go to a LinkedIn size and we're doing 1.2 petabytes of events a day, right? We're not going to be able to do those kind of queries. You can set it off, go home, come back next year, and it might be completed, right? So just simply as easy as that. And the problem is this, right? We have the only way we can determine whether an event or a message is valid to the query that I've submitted is by reading that event or message. So, company dead, we shut down, we go. That's not quite what we did, right, as you can imagine. This is the perfect example. If we think this is our Superset or our Tableau or our Jupyter, we're going right to the beginning of my topic, reading everything through in order to create my query. So how do we fix it? Well, we cheated. Definitely cheated. Turns out that some really, really smart people have done about 30, 40 years of work on making databases queries quite quick. So we just borrowed some of their techniques. So to make predicates faster, for instance, we borrowed indexing. To make grouping faster, we borrowed pre-aggregation. To make joins faster, we borrowed topic statistics. We applied all these techniques on top of the event streaming system to create something that looks a lot more like the conventional data lake that you own. No one going to push me and ask how it's any different? No? Okay, I'll do it myself. How's it any different, Tom? Well, the key point is these are all additive technologies. We haven't moved or transformed the data in any way. We're still running our real-time system as the single source of truth, as the operational system always should be, in my opinion, and many other people's opinions. All we're doing is enriching that data set in order to be able to offer the kind of query performance that makes it useful for the analytical side of your business. The result? All the data. Every single piece. So every single data scientist we've ever shown this to has gone, holy crap, I had no idea there was so much data available in my organization that I'm not using today. And it's the rawest form of data. I put this here as a plus. It may not necessarily be a plus. It's kind of like when you open the Ark in Indiana Jones. Just be aware of that. It sounds great, but it is typically for our microservices architectures for our data-driven companies. This is typically the point at which data is ingested. The first thing you do with it is put it in Kafka so it can then be served out to your other services. So it is the rawest form of data and the highest volume form of data, to be honest, that you can get in your system. It's also the biggest variety that you have access to as well. I want to make, I only mentioned it once, but I want to make a really good point about graceful reactions to change. If we go back a couple of slides, we go back to our thing here. What happened? This is the operational side of your business. It's built to make your front ends, make your applications work. Therefore, it's subject to change, and it should be subject to change independently of these analytical systems. Right? Kafka does some wonderful things around evolution of message shape and message content, and because we are querying directly at the source on the real-time data, we can take advantage of all of those. So if somebody adds an extra column to your event, it just suddenly flows through. Someone changes the type of the column on the event, you can instantly take advantage of that in your interactive queries. We talk about this as interacting with real-time data at human speed. Right? We are looking to be able to make it, well, to be honest, a delightful experience. That's what we want. We want people to be able to dive into the real-time data they have and explore, play around, see if you can. That's the experience that we're looking to create. And finally, because it wouldn't be real time unless you were getting the latest data set. We are operating on the data without moving or without transforming it at its point of creation. So as soon as it's created, it's available. No more waiting the day for the data set to go through your batch pipeline. No more waiting the hours for your polling job to be done. The second it's created, it's there. And yeah, we think it's pretty cool. So that's the first half. Please hurl questions and abuse at me. I appreciate it. And I think we're going to have a little bit of pizza before I hand over to Pradeep to show you this in action and with real data science models.
Hi guys, I'm Pradeep. I'm a developer advocate at Streambased. And Tom's my boss. I never expected this was not the speech. We did it 2 hours ago. He's really good in the live presentation. He's really, really good. I was blown away. So I don't know how I'll live up to his expectations. See. Okay. First of all, I'm gonna show you a live demo of how Streambased is going to be, solving all the challenges that is, involved in real-time data processing. First, we're going to see what are the challenges, and I'm going to go in order. First is the discovery. Kafka not in the catalog, and no one is using Kafka. No one is aware that Kafka can be used for retrieving data and using it for analytical purpose. And then EDA, when you have to exploit find what the relevant data that has to be used in the modeling, but sometimes you don't get the relevant data because you don't know what are the data that is present. So you have to know what is present, and then you have to sort the EDA stuff. And then the third challenge is latency. As I think all people are using old data. We don't need old data because you don't need to use a data which is like 2-3 days old in order to do real-time processing. That is not real-time processing. We need instant data that's available in seconds. So yeah, third thing, even if you solve discovery, EDA, and latency, you're going to screw up. There's a lot of screw up with integration because for solving specific problems, the data scientists, data analysts use specific tools. Sometimes they'll use Power BI to showcase a dashboard, and sometimes they need a Jupyter notebook in order to do modeling, show the story of how they came up with the solutions. So they can screw up with the integration because the ETL pipeline will be specifically built for certain apps. So these are the general challenges in real-time data processing, and in order to solve it, we are going to use Kafka, as my boss explained to you, using Streambased, and everybody universally uses Jupyter for telling a story of how they came up with. That's very common. I think everybody would be surprised about what is this one. This is called River, an online machine learning package, which is used, it's a Python package. The unique thing about River is you're not gonna, it's called online machine learning, platform, because it's not going to use a training model from scratch. You're not going to use a training model from scratch, and if you come up with, you come up with the data streaming, the data will stream new data then and there. You'll get new data. If you get a one particular kind of data this day, the next day you're going to get new data. So you're not going to train from scratch and improve the data modeling. So what you do is that's where River comes. The new data is streamed into the data model, which is modeled with the old data sets, and the new data set is going to go into the old machine learning model and incrementally learn from last new data. So you're not going to start over every time when you model the data. That's what unique. That's what is unique about the River package. And for this demo, we've used a business case of as Tom previously told you about banking, about how Kafka works in the banking, and we are going to take a similar use case. We're going to do fraud detection. We have we have produced transaction fraud markers such as multiple international transaction addresses, and these features are used as markers in order to predict if the transaction is fraud or not fraud. What is unique about using an online machine learning for this use case? The fraud, the fraud detection, there are new types of frauds that are happening. And when there are new types of frauds, the machine has to learn quickly and adapt itself in order to find out what kind of fraud, and in order to detect it, much quicker. And you don't need to detect a fraud 3 days after the fraud is done. You have to have an instant, you have to come up with instant solutions and take actions on it immediately. So this is one of the very interesting use cases. So we are going to see this use case, and a specific machine learning model that I've used for this demo is Hofding tree classifier. It's not a tree classifier, but as I told you, the only difference is you're going to stream in the data first, and the model is going to model, and again you're going to ingest another new type of data, new data that you got from from your data stream, and it's going to learn from this new data and improve the old model, and it's going to incrementally learn as the time goes. This is the unique thing about the Hofdinger tree classifier. And now it's time for the demo. So, and where is it? Oh. Okay. Now we have a data. Is it visible? Yeah. Okay. So we have a data set which, as I told you, we are going to find the fraud detection. We're going to predict the fraud detection. And what is the most unique thing about Streambased is you're just going to connect the Kafka using the SQL server, a JDBC connector, and then you're just going to give an SQL query in order to retrieve the data. To get the data from the source to your Jupyter notebook. It's just an SQL command that connects to the Kafka and retrieves the data. And as you can see, yeah, we have put the data into our data frame, and as I said, package for modeling the data, job is not to save model. As I told you, It's equivalent. It's not, a model for you. Take the whole data set, dump it into, the model and it learn. It's not one by one. And unique thing about using the framework is it works better one row at a time. It's the most about that river. So it's instantly building up models and instantly building up versions of those models. Build up versions every day. For predict fraud every day. Just to use it in deployment and find out what is the fraud that is happening instantly, and taking some actions immediately. That is a plus point about using the river package. And yeah, this is the modeling part. And as I told you, there is a predictor here, which is very similar. You're going to load the data, and we have saved the model. So using job load package, we're going to use the saved model, make a predictor from it. So you see, it's very simple. We've never used a data engineer. I didn't go to a data engineer and ask me dump it into a data lake. Then I can pull it up. Then I can analyze it on top of it and make a model. I just did it by myself in half a day. The whole thing, from ingestion to modeling to a predictor in just half a day. And how many lines of code you've seen now? Maybe 100. That's even a simple ETL pipeline is gonna make you have to and dozens of codes, and it's going to involve a lot of manpower for processing, and it also increases your memory. Duplication happens everything using Kafka index, and these kind of new action insights out of the results that you're gathering from it. And we can go back to the slides again, I think so, yeah. And this is the final overview. As I told you, and as Tom also told you before, these are the producers of data. It's going to directly stream into the clusters with Streambased in it. And here the JDBC connector, which retrieve data just by using the SQL command into a unique type of tools. It's not only Jupyter. You can use Power BI, Tableau, set anything, and it's that simple and that easy. And as I told you, actually last week we went into the big data and AI world, and we got into really huge trouble because we were handing out flyers with #NoAP. It was a protest. And I explained. Oh, one joke over here. Okay, good. Okay, now. Since
Slide. So, your mission. We always like to leave you with something to do because why should I do all the hard work? Your mission, should you choose to accept it, is to go back to your business. We've all discovered that we probably are fed a lot of data from real-time systems. So let's go get it. Go back to your business, get some Kafka credentials, and go and explore. Have some fun and gain some insight.
Now, for our final talk of the evening, Michael talking about a survey of AI in practice. Thank you, Michael.
Okay, thanks everyone. So just before I get started, the motivation behind this was roughly this time a year ago. I had a couple of conversations with people that I know are very conservative when it comes to machine learning and AI, and think that everything that a human generates is perfect. And the next thing back is sort of if-then statement, maybe hundreds of thousands of them. That's good. Everything to do with machine learning is maybe not so good. And then about a year ago, I had a whole bunch of conversations with these people that said, why don't you just use ChatGPT for it? Okay, so that's interesting. Why would you say that? And then the answer was, well, because everybody's using it. That's weird. Where does that? I mean, I love everything around large language models. It's amazing. I mean, it's just people build companies around this stuff, and it's great. But that doesn't mean that everyone's doing it. And so I thought, okay, let's ask people what they actually do. So this is really what I want to do. Do this, what happens in practice. So I want to know a little bit about the people who are answering the questions, obviously, so that we get some understanding of who says what. Then some questions around the models that people are using, and the data, and how they think they're doing MLOps. That's so. Before I get to the surveys, a little bit about sort of the respondents. I had hoped for about 10,000 survey responses. I'm not there yet. I started it really in July. I'm about 8.3 thousand now. And they come from various sources. I started sort of 2,500 roughly that come from friends. Obviously, I don't have 2,500 friends. But it's sort of friends and friends of friends and colleagues of colleagues. So I would go to somebody and say, can you send the survey to your team? And all of a sudden there would be 100 responses coming in from Hong Kong or something like that. It's that kind of thing. I went to about 30 conferences and meetups last year and showed them the QR code. So I have another roughly 2,000 that. I did one LinkedIn post. That's just one post that by itself, bizarrely, within a week generated just over 1,000. And then I did paid ads because I'm stupid. The click-through rate is less than 1% on the paid ads. So the paid ads on Reddit, on LinkedIn. I started with Google and Facebook, but I stopped them very quickly because nothing came, or nothing sensible really came. So I still keep the LinkedIn campaign running at the moment. The cost per click is terrible. It's just over $1. I have a conversion rate of about 13%. So you can tell how much this thing has cost me, but it's just not. So anyway, so then I'm really quite happy with the geographic split. It's fairly broad. I think I want more people from the US. And what surprised me is I thought the people in the market here, really large companies, would be much bigger. That was really small, so I don't. Most of the people who are responding really come from startups and small companies, which is great. It's actually amazing, but I really was hoping to get more of these people to get my original argument. So anyway, on to the data. So the first thing that I ask people, one of the who are you, is what do you actually do? Do you manage, or do you actually do stuff? And it turns out it's the first it's the first of many bimodal distributions. So you have people, and actually it's kind of, at first I was surprised, but it's kind of cool that nobody just does stuff anymore. I think that's sort of a very 1990s mode of working. And everybody seems to be doing a little of managing, but you have some people who spend most of their time doing, and some people who spend most of their time managing. And we'll come back to this one later. But to the heart of this thing, which is sort of what do people actually use? And this is now the 8.3 thousand responses sorted by what people are using in production. The 100% bar is just above this one here. What people are using in production is the black one, so in decreasing order, and then what they experiment with. Because I've asked the two things in separate questions. And it turns out that people love boring stuff, which is not surprising. This actually good old linear regression or whatever it is the workhorse of a lot of statistical learning, and that's what's in production. Obviously, people don't get excited about it. They don't want to experiment with it anymore. Then you have XGBoost and all this kind of stuff. That's sort of second place. Then comes all the deep learning stuff, excluding LLMs. And by the way, in the comments, I got hate comments for putting GANs into this bucket as opposed to that bucket, because everybody said, oh, but it's generative AI, you need to put GANs in here. Anyway, I'm not sure how many people actually use GANs in production anyway. But anyway, so then sort of all the other methods sort of following in, and then obviously comes the one that's sort of interest, which nobody virtually uses, this is about 3% roughly. I think roughly 3.5% or so of people said they're using large language models in production, but virtually everybody does experiments with it, which is kind of cool. I mean, that's actually super exciting. And getting that made me just supremely happy, because what people confuse is that everybody's talking about it. This is, but actually very few people are doing about it, which we intuitively all knew. But now we have about 8,000 people who are telling us that that's exactly what they're doing in the real world. So that was that I really liked. Then when I asked a different question, so this question is, tell us everything that you're using. So some people actually ticked everything, which is also obviously is mildly suspicious. Then I asked, okay, what is the most important one for your organization? Select just one. And there I found that I did not expect. So there the XGBoost stuff comes out and the large language models. So when people say what's really important for us, I think there is an appreciation that this stuff has some kind of relevance. Maybe not yet today, but maybe later this year with whatever next versions come out. And maybe the year after that. I thought that was sort of an interesting one. We had another bimodal distribution. So then I said, okay, on large language models, what do you actually do with them? And I gave them those categories, and I'm not quite sure whether those categories are good, but they essentially fall into a couple of things. So everything around coding is these four here, sorry. Then I said text, which is sort of the ChatGPT type use, images and all sort of Midjourney type use, and anything else that you can think of. And on the coding, I split it out into, do you help yourself to code, sort of checking things sort of Stack Overflow style? Do you actually run a Copilot kind of environment, which a lot of people did? I think that's about a quarter of responses. Do you use it to generate data, which I thought was actually one of the few really useful use cases, which nobody does. Then do you use it to sort of build initial prototypes or frames of stuff. People like using it for coding in production. I don't even know how you would put Stack Overflow stuff into production. So I think that's kind of a stupid question, but people answered it anyway. So people use this. They don't use that so much. And what I found interesting, if you compare it again back to this slide here, where we said, what do you use in production? Whenever almost every single one of the people who said, I'm using it for Copilot style, they said, we don't have LLMs in production. So there's clearly sort of some kind of dichotomy where people are thinking of a production system that does something useful, or I have a system that helps me code. And in my mind, they're kind of different. So people say, I have Copilot in production, but don't actually accept that they have an LLM in production, which is kind of interesting. I think that's also the backdoor kind of way into our workflows is going to be how perniciously LLMs are going to be everywhere. Anyway, so then I said, let's go to data. As we've done model, let's go to data. How do you rate, in a very fluffy question, how do you rate the quality of your data from useless to really, really amazing? And so again, another sort of bimodal distribution. And when I saw this, I was surprised. I don't know about you, but data in my world has always been terrible. It's never 7. I mean, gee. So I thought, this is kind of weird. So I looked at, obviously, so now we have lots of demographics about people. So I thought, okay, let's have a look at one of those. Actually, I looked at a whole bunch of them. But this was the most interesting one. So I looked at, do you remember, I asked people whether they're duo managers. I said, okay, everybody who's a 6 and above, manager, 5, I don't know what you are, and everybody 4 and below is a doer. And I hope you know what's going to come. And it's this. The doers say, our data is terrible. And the managers say, our data is amazing. So, and they're probably in the same team. So that one I really loved. That is just organizational reality on PowerPoint. So anyway, I said, how well is your data labeled? That's interesting. That's not a bimodal distribution. I think that's sort of uniformly bad. I think it's the answer. And then I asked, how much data do you actually have? Because obviously, we all know that internet scale and whatever else, which is sort of here. But actually, this was sort of a we've still seen some of the mode of this distribution is gigabyte sort of side. That I thought was a good sanity check. So then I asked a whole bunch of questions about MLOps, and I'm not going to give you the individual responses because they're almost invariably sort of bimodal distributions, and there are some differences between large companies and small companies, and all these organizations, all this kind of stuff. But obviously, how do you think your production systems actually are? What's development, deployment, monitoring, and governance? The only one that is not a bimodal distribution is how do you rate collaboration and communication with the team? That is uniformly bad. And that was actually kind of a shocker because we kind of intuitively know that this is the case, but to see it come out so strongly in the data, that I was really shocked by. That everybody says, it's kind of terrible. I also asked people's jobs. What do you actually do? And I gave them a very long list that they could select from. And then I said, who do you collaborate with? And that's very interesting. You see very interesting clusters of behaviors. I think I have a slide somewhere. I didn't put it into the stack because I don't think it really adds that much. It's a very confusing who collaborates with whom diagram. But clearly that's lacking. Then my last one is this one. That was the question under the MLOps section of what proportion. I asked how many prototypes do you have, how many pilots, POCs, and everything else, and how many systems do you have in production. Basically, you can work out a proportion of how many pilots go to production from that. I asked explicitly, prototypes, pilots, POCs typically move to production, and that. Again, there's a lot of truth in this and something a lot that I recognize. I just thought it's mildly depressing that pretty much more than half of all prototypes that are developed never make it into production. That's kind of more than that. That's sort of what's coming out here. A third, a fifth of all the work that you do, you work 5 days a week, but only Monday actually goes into production. Tuesday to Friday is going thrown in the bin. So that's kind of depressing, and I think there's a lot on the MLOps side that can be done. But I think that's the reality. A lot of the work that we do is still very much experimental and not that firm. But again, I thought it was an interesting result to share. I'm not yet done. I still want another 1,700 responses, and if another 4,000, I'm not going to be very happy. So please give me some responses. Thank you.